I'm not paranoid. They pretty much just told me they're going to hit me in the face with a pie. So I would be an idiot to come to the math formal. No, I'm not coming to the math formal to get hit in the face with a pie.
Come in your twin brother's Walmart outfit.
I'll just send my son as a representative. Here, hit Daniel in the face with a pie if you must. There you go. I'll begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for the student and for the students that will watch this later. Help us to glorify you what we do and understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. So today we are trying to wrap up the material on metrics, well, at least for the moment. So like chapter, you should understand what this book is. What this book is an introduction to manifolds, right? Like the title says, Introduction to Smooth Manifolds. So it's not the end of what there is to say about metrics by any stretch. It's just, this is the basic thing, right? And so like corollary 13.30, every smooth manifold with or without boundary is metrizable. So that's a very interesting result. So earlier in the chapter, that partitions of unity argument, I think worked for a connected manifold that proved that we could build a Riemannian manifold basically by pulling back the Euclidean metric on the parameter space back up to the manifold, and we can patch it together smoothly using the partition of unity. And then this corollary 13.30 on page 341 basically extends that to manifolds which are like, not connected. They're different pieces, and it's got this kind of sneaky equation. The distance from x to y is the distance from x to pi plus 1 plus the distance from pj to y. So it's got this like sneaky thing it does to bridge the components. It kind of defines there to be a length 1 distance between token points, I think, in the different components. And it turns out that if you do that, you can, from that, have a distance function which is defined on the whole manifold, and as such, it's metrizable in the sense of there being a metric. So I'm not sure your topology will be. I'm not sure this is something your topology course would get into, but there are some topological spaces which are metrizable, and there's some that are not, because every metric space has very particular topological properties, like I believe it's Hausdorff. Like metric spaces are very nice topologically, and comparatively, so there are other more exotic topologies out there which are not metrizable, and they're missing various bits and pieces of the beauty, which is metric topology. And there's a whole story there about like T1 versus T2 versus T3 versus T4 topological spaces, and I think that used to be a much bigger part of the discussion in topology courses. Like now, I think we're getting more to the point where topology is something we need to use to apply to other problems as opposed to just being an end unto itself. But anyway, so this is the tangent-cotangent isomorphism, also known as the musical morphisms. So this is some of my favorite stuff. And basically, so we're talking about a Riemannian manifold. And G hat is essentially an isomorphism, a bundle isomorphism from the tangent bundle to the cotangent bundle. And the way this is done is that, well, here's the specific definition. G hat of V of W is equal to G sub P of VW, and this is for all V in TPM. And here, where's the W? Oh, the W's in, well, V and W are both in TPM, of course. So sometimes you'll see this written like, this is how I tend to see this written. Well, I don't know if it's written exactly like this, but something like this. V, comma, and then there's a blank here. I mean, that's essentially what's going on. Is you're just not using, you're just leaving one of the one of the entries unused. And so that gives you a way to take a vector and get a corresponding covector. See, because this is naturally linear on W. So that's a covector because it's linear on vectors. And so here, let me read this like super smart paragraph. Because g hat x of y is linear, so you can define the same for one other formula here. For vector fields, like what if we feed it a vector field? G of vector field x acting on vector field y is equal to g of xy, and that's for all smooth sections, for all vector fields, if you will, on the manifold. All right, so as he points out, because g hat xy is linear over the smooth functions in the manifold as a function of y, it follows from the tensor characterization lemma, aka lemma 12.24, that g hat x is a smooth covector field. Because g hat x is linear over the smooth functions on the manifold as a function of x, this defines g hat as a smooth bundle homomorphism by the usual bundle homomorphism characterization lemma, which is 10.29 from the chapter reading cover. And as usual, we will use the same symbol both for the pointwise bundle homomorphism, g hat, and the linear map on sections, g hat. So, I mean, this is the pointwise, and this is the on section. So it's the, yeah. All right. And so just let me rehash some things here. So g, right, we can write as the sum I and j of like gij dxi tensor dxj, right? And, oh, in fact, I can just scratch the tensor because it's symmetric, right? If I recall correctly. I think we had that formula. So, lovely. And so if you look at this, let's see here, g of xy, what's that look like? Well, the formula for that is sum over I and j of like gij. What happens, like, for example, what's dxi of x? Well, that's just x upper I, right? That picks off the ith component of x with respect to the local basis, the local coordinate basis we're using. So we just have x upper I and then y upper j. So there's a formula for it. Well, there's just a formula for the metric acting on a pair of vector fields. All right, so let me continue down this notational exploration. I have to get used to his notation. So here's what he says. He says, so apparently g hat x we should think of as having the following coordinate expression. Like, I'll put the sums in, right? He doesn't. That's cool. Like I said, without the repeated index notation is the physics notation, and that's not a bad thing, but I'm putting sums in, so there they are. Sum over I and j, gij, x upper I, and dxj. Or you could simply write this as the sum over j of x lower j dxj. Now that's a sneaky thing I did right there. Definition, x lower j is equal to the sum over I of g I j xi. So in the physics literature and elsewhere. This is called lowering the index. Lowering the index I. All right, so we've lowered that I index down by contracting against the metric. So, yeah. So this is the first place one of the first places I ran into tensors was when I was taking a class in special relativity, and we were like raising and lowering indices like this. All right, and so I was like, what are we doing? Why does it work that way? And we kept asking the professor, like, why does the metric lower the index like that? And he's just like, and he would just repeat, that's what it means to lower the index. And we were like, but why? And finally, after about the fourth time we asked him, he's like, there's a professor over in the math department who really cares about these things. You should go talk to him. Something like that is what he told us. And that's how I met my future advisor, by asking this question, essentially. So, so here's the deal. Yeah. There is something else. So like if G, well, let me use some citation here. If the sum over K of G upper I K, G lower K J is equal to Kronecker delta I J, then G upper I K is the so-called inverse metric. Now, be careful, it's not an inverse. It is not an inverse in the sense of it's an inverse to the metric. Like the metric is a bilinear form from the reals, bilinear form from the Cartesian product of the, it takes in pairs of tangent vectors and gives you back a number, right? Locally, and there's a smooth assignment of those over the manifold. That's a metric. So when I say inverse metric, I don't mean inverse in the sense of that function. I mean inverse in the sense of the matrix of the metric at each point. This makes G with the upper indices the inverse matrix to that. So, all right. So if you have one of those, then you can also make another definition. Definition, given alpha in, I don't remember my notation for it, but goodness gracious, alpha, let me just write a formula. I forgot the home. I forgot what the name of the home is for these guys, but suppose you got alpha of alpha sub I dxi, right? So this would be a covector field on the manifold, all right? Then alpha upper I is equal to a sum of G upper I j, j alpha lower j. This is, what I've done is I've raised the index. Raised the index on alpha. So let me recap what's going on here. I've started with a contravariant vector which has an upper index, and by contracting against the metric I find the components of a covariant vector, a covector. Vice versa, if I contract with the inverse metric coefficients, I can raise the index. I can go from starting with a covariant vector and get out a contravariant vector. And these operations are reversible. So if you raise and then lower the same index, you're right back where you started again. These are the musical morphisms at the level of components. So essentially this is, let's see here. So I think the flat map is essentially we take in the vector field and we output g hat of the vector field, right? The sharp map, which I I always forget how to draw a sharp.
It's like a number sign.
It is like a number sign, but it's a little bit not. It's got a tilt to it. And so like the tilt is it goes the other way. So it's like, I don't know if does he have notation for it? He just calls it G hat inverse. So alpha goes to G hat inverse of alpha, right? So like this is literally the sum. Oh, maybe move my camera. Move my camera for Mr. Jeff. I assume he watches these. Let's see here. Where was I? So here, this is, sum over whatever index, whatever letter you want to use. Let's say J. Sum over J of, x lower j dxj, right? And this, on the other hand, would be the sum over, let's say, I of alpha upper I partial xi, right? Explicitly, what that means is the sum over I and j of, g I j x upper I dx upper j. And this is explicitly the sum over I and j of g upper I j alpha lower j partial xi. Now, fortunately, we can be kind of like sloppy about which one's the I and which one's the j because the metric is symmetric in the ij index. All right. And likewise, the inverse metric is also symmetric. Like symmetry of the matrix forces symmetry of its inverse. So yeah, those are the musical morphisms. And you can, we can prove that we can prove that that's indeed an inverse, if you like. We can prove that if I take the sharp of the flat of alpha, well, that's the sharp of, what? Flat of alpha, which is this thing. Sum over I and j of gij alpha j partial xi, right? But then, by definition, the flat, right, what does it do? It takes the sum over, let me use a different letter, let's say L, right? And let's see here. Let me use some notation here. So oh goodness gracious, I don't know if my brain is good enough for this today. Sum over, golly. Let me just make an in-between step. I think I'm getting sick at the moment, so just a warning. You might have a vacation from me Thursday. Let's see here. So let's call that thing like, y upper I, right? That's y upper I. So the flat says you do y lower L, right? And then dxl. That's what the flat says. It says you take the component of the vector that you're flatting, and you lower the index, and you can you contract it against the coordinate system you're using. But how do I actually lower the index on that? So I've got the sum over L and let's say K of, well, that would be G LK of y upper K, right? That's the definition That's what we mean by y sub L, right? But now let me go back to what y sub k actually, well, y sub k is. So I got to do this. I replace the I with a k, right? So I've got the sum over L and k of GLK, and then my YK is actually the sum over I and J oh, goodness gracious. I guess I have to do the sum over K and J? Man, that feels wrong. Oh, I have a bad feeling. Doesn't feel right. I should just have the sum over J, not the sum over I. I should just have the sum over J. Because the sum over I, like this, I should think of as like the sum over I of yi partial xi. That's what should go on here. So I shouldn't have the sum over J in this. I should just have the sum over, I shouldn't have the sum over I in that. That's this. I should just have sum over J. And that I has to be not summed over, but in fact K. So, well, I honestly, Preston, like I didn't think I was going to make it out of that hole. I'm kind of surprised. Pride cometh before the fall. Watch me mess it up. Let's see here, J, alpha sub J. That's my y sub K. And then I've got this dxl. All right. Okay, so what's the deal? Well, let's reorder the sums. We're going to take the sum over L and the sum over J and put them out front. And then we've got a sum over K we'll put inside. We can always flip sums around, and we can move this inside that sum without loss of generality. That's just properties of finite sums. So like that. And then, of course, you got yourself alpha sub J and dx upper L. But by definition of the inverse, by the inverse metric being the inverse metric, this right here is precisely Kronecker delta Lj, right? Which squashes one of these sums and just leaves us with the sum over, let's say, J of alpha J dxj, also known as alpha. So that, in a nutshell, is why it is, in fact, an isomorphism, because there's this inverse. I mean, he has more supporting evidence in the book, but yeah, these are the musical morphisms. Because they're raising and lowering the indices. It's horrible, isn't it?
And it's just the person who invented likes music.
Yeah, I think the name musical morphisms came decades, lifetime, probably a lifetime after the inventor of this. I don't even think musical morphisms is like Misner, Thorne, and Wheeler, which is like this, this big book on gravitation from the, I don't know when that came out, like 65 or something, 70, somewhere in there. You can talk to Dr. Zygombortis. He had a general relativity class out of that book. So did I. And I don't believe the musical morphism. I mean, the musical morphism is in there. It's definitely in there, but I don't think it's called the musical morphism. So, like in fact, in Misner, Thorne, and Wheeler, the basic philosophy that's used is that if you've got a tensor and it's got inputs, say it takes two vectors as inputs, you can change that tensor and make it take two covectors as inputs, or you can make it take one vector input and one covector input, because what you can do is you can just use these musical morphisms to change the inputs from vectors to covectors or vice versa. Like, you've got all the flexibility in the world to change a given tensor to a different type that's related through a composition of these morphisms. And so they take the viewpoint that those are the same tensor, which is, you know, a little bit to get used to if you're relying on a tensor being a specific multilinear map with a given domain and a given codomain. Like, that's not how the physicists think about tensors, at least in Misner, Thorne, and Wheeler. But anyway, that's what this is. And another really cool application is he actually has a formula for the gradient. So, like, here's the gradient of a function, a smooth function on a manifold, Riemannian manifold, obviously. He's like, we can just say it's df, which is a covector, and then sharp that thing. See, that would be, what would that would be, you know, g hat, in his notation, g hat inverse of df. And he's like unraveling the definitions. He points out that if you have the gradient of f and you let it take the inner product with x with respect to the g metric here, that is, let's see here, he says g hat of the gradient of f of x, which is, so if you compose the g hat with the g hat inverse, you're just left with df of x, which, by the way, is x of f. So that's kind of cool. And he even gives us a specific instance of this formula. So like in Rn, well, not in Rn, but here's a more detailed formula for it. So like grad f in a particular coordinate system, we'd have the sum over I and j of the inverse metric, gij, partial f, partial xi. Those are the components of df, right? That's df sub I, and then partial xj. There's actually a formula for the gradient of a smooth function on a manifold. That's kind of neat. And he actually puts this into practice for the polar coordinates. I have a little bit more to say there, a little bit that he doesn't. So like application m equals to R2 polars. So what do polar coordinates, so like, I think we worked this out, right? We could either write g bar is dx squared plus dy squared, right? Or you could write it as dr squared, right? Plus r squared d theta squared. I think we worked that out, right? You have these two different choices for expressing the Euclidean metric on the plane, if you like, ignoring the the coordinate defect at the origin for polar coordinates for a second. So, all right, so like in polar coordinates, so if we talk about gij, and let's just, I don't have a good notation for it for polars. Well, the matrix is 1 and r squared, right? So what's the inverse matrix then? How do you invert a diagonal matrix?
A diagonal would be inverse of 9.
Mm-hmm. So what's 1 over 1?
1.
1. And 1 over r squared is, well, 1 over r squared, right? So obviously we're going to get into some trouble at the origin, but we're agreeing not to, we're staying away from the origin, right? Just a bunch of troublemakers there. And so putting that into practice, what we got the gradient of a function in terms of polar coordinates then is, let's see here, we've got, so there's 4 possible terms in this sum, right? But only the 1, 1 and the 2, 2 matter. The 1, 1 gives me 1, and then partial f, partial r, partial r. And the other one gives me 1 over r squared, partial f, there's an, my bad. No. Partial f, partial theta, partial theta. That's the gradient of f. Now, in my calculus 3 notes, I write the following formula. I say partial f, partial r, r hat, plus 1 over r, partial f, partial theta, theta hat. I say that this is the proper formula for the gradient in polar coordinates. In fact, that is the formula you'll find for the gradient in polar coordinates. In, like any junior level physics book, you'll find this. So what's the situation here? The situation is basically that this partial theta is not a good basis. Like, it doesn't give us an orthonormal basis. So what we want is like partial r for the one basis. And so basically this we can identify with r hat. But we have to throw in a 1 over r for the partial theta for the theta hat for dimensional reasons. And so with that adjustment, there's your gradient in polar coordinates. If we were to do sphericals, why not, right? In 3 dimensions, g bar is, d rho squared. The connection between sphericals and the usual math polars is rho is equal to r sine theta, right? Or sine phi? Sine phi. Here's the picture. So sine is the opposite. This down here is rho sine phi. Z is rho cos phi, for what it's worth. And so when you take dx squared plus dy squared, dx squared, like this, the dx squared plus dy squared still gives you r squared plus r squared d theta squared. But you could change to rows like this. And anyway, what you end up with is d rho squared plus, you can figure it out by just sort of like geometrically imagining. Like, suppose you sweep out a little, if this is phi, right? And you just fix the rho and you fix the theta, but you're sweeping phi. What's the little bit of arc length subtended here? ds is what? It's like rho d phi. See that? On the other hand, if you think about sweeping out a little theta, it's like fix the phi, fix the rho, sweep a little theta, then your ds is like r d theta, which is rho sine phi d theta. And of course the d rho, well, that's easier to think about. You just sweep a little d rho, ds is d rho. So in these 3 different special cases, we have these. And when you actually work out the calculus, it verifies the geometric intuition that this should be rho squared plus rho squared d phi squared plus rho squared sine squared phi d theta squared. Again, this is for standard math sphericals, like you'll find in the mainline calculus books. So listen, long story short, what's the metric in sphericals? It is 1 rho squared and rho squared sine squared phi. If I order my coordinates, rho, phi, theta, which I think is the proper way to do it. Because if I think about phi hat and I cross it like rho hat crossed into phi hat, yeah, that's the right way. Rho hat crossed into phi hat should give me theta hat. If you visualize that, it checks. This makes it a right-handed coordinate system, this ordering. That's your metric. What's your inverse metric? Well, that's the beauty of using an orthonormal coordinate system, is that the inverse metric you just flip. And of course, like in general, it's not like that. I mean, there's uglier stuff that happens in relativity because, for one thing, you're not working in Riemannian geometry, you're working in semi-Riemannian geometry. But another thing is you're not always blessed with a pseudo, whatever the right word is for a, it's not orthogonal, but the analog of orthogonal in the semi-Riemannian case. I guess it would be, we probably just still say orthogonal with the understanding it's modified. But there you go. And so like the gradient of f in this context would be, so you got like partial f, partial rho, partial rho, right? And then plus 1 over rho squared, partial f, partial phi, partial phi, and then plus 1 over rho squared sine squared phi, partial f, partial theta, partial theta. And this can be rewritten as partial f, partial theta, partial f, partial rho hat, plus 1 over rho, partial f, partial phi, phi hat, plus 1 over rho sine phi, partial f, partial theta, theta hat. That is the gradient in terms of the spherical coordinate frame. I had to absorb dimensional factors into the theta hat and the phi hat, exactly that same thing that was appearing in the corresponding diagonal component of the metric. One of them goes to the formula, the other one goes to giving us an orthonormal basis, a unit frame. So, and this formula you will find in junior level physics books. Where you won't find this formula is Stewart, because Stewart is a poor Calculus 3 book. It just is. They all are. Yes. Calculus 3 is an afterthought for all of the mainline calculus books, unfortunately. It really is. I'm told that there is a 1,800-page calculus book written by a couple of professors at NC State. I haven't got my paws on that yet, but I have a suspicion that that book has got a proper Calculus 3 in it. So if I could just get us to switch to that 1,800-page calculus book. So Dr. Norris at NC State had a hand in that. Dr. Norris's Calculus 3 is at least twice as careful as my Calculus 3. Although he might not bother with this stuff either because he's older and wiser than when he did it. I don't know, but all right. So that's the musical morphisms, and there's a couple of down-to-earth applications to Calculus 3 in terms of like how to derive the gradient in other coordinate systems. If you do that directly, it's just chain rules. It's chain rules and also going through the trouble of figuring out what should theta hat and phi hat and rho hat be. There are natural ways to derive that in terms of multivariate calculus. You could calculate the gradient of those functions because you can write a formula for theta, for rho, for phi as they relate to x, y, z. So you can take the gradient of those. That gives you a direction. That gives you a gradient vector field of the coordinates that points in the direction of like increasing rho or increasing theta or increasing phi. And then all you have to do is take that gradient field and normalize it. And that will give you rho hat, theta hat, phi hat. That's a concrete calculus 3 way of doing it. And that's in my notes. But this is slick. This is really slick. And Dr. Skimbortis tells a great story about this and the time he tried to do this in a junior level mechanics course here. You could ask him about it. It's a funny story. The students revolted. They're like, no, you can't do this. It's too pretty. Only show us ugly things. That's not what they said, but did they say, will it be on the test? Ah, yes, nothing gives me joy quite like that. So let us move on. I think I've said my piece about this. There is more to say about this, though. There's actually a natural extension of this to differential forms, and I don't think all of that material is actually in Lee. So let us forge ahead boldly into chapter 14. Which is on differential forms. All right, so what is a differential form? So we're on a manifold, all right, and I'm not going to start by assuming we have a Riemannian manifold, but what I was just blathering about vaguely was if it's also a Riemannian manifold, then there's a really neat extension of the musical morphisms to differential forms. And that's exactly the stuff that's used in the gravitation book I was talking about. But anyway, so I don't want to write all this stuff down. I'm just trying to pick the high points here. So here's a definition. Alt alpha is equal to 1 over k factorial sum over the permutations on k indices. You put your sine of sigma up in there, and that sigma alpha notation that we talked about before. All right. So explicitly, I guess if I write this formula down, why'd I even bother write the other one? But here it is. I'll write it. Here's explicitly what that means. Sum over the permutations. What you do is you stick the sign of the permutation out front, which is going to be plus or minus 1. All right, and then you take alpha and you feed it. Oh, rats! Oh, son of a gun. All right, let me erase the equality here. You'll forgive me this manga style comment. So alpha v, I'm not going to erase it. I'm going to save it by writing left to right. I mean right to left. Sigma k, rat. I don't know why I'm writing this. Anyway, this is alt alpha acting on a k-tuple of vectors. All right, so basically what it does is it shuffles the inputs. It shuffles the inputs to the tensor, and it adds pluses or minus according to the shuffling. The difference in the symmetric material is that we shuffled all the inputs, but we just made it all plus 1. Right? So now it's got a plus and minus going on. So like, so some specific instantiations of this. So like alt beta, alt a 2 tensor, beta a 2 tensor, alt beta of VW is equal to beta of VW minus beta of WV. That's it. And I seem to have forgotten a important what? See that? So I need here k equals to 2. So the way this formula fleshes out, like what is S2? S2, it just has two things in it. It has the identity element, and it has the permutation which sends 1 to 2 and 2 to 1. It has the eins element and the permutation which maps 1 to 2 and 2 to 1. That's it. That is the symmetric group of order 2, which happens to also have order 2. There's two things in it. And so this sum over permutations, like the sign of E is 1, the sign of 1, 2 is minus 1. And that's the formula. This is the only one I'm going to explain in detail, okay? Because by the time we get to 3, I don't want to teach you like cycle notation for S3. We should leave that for your abstract algebra course. But here's the formula for 3 things, alt. And you can kind of recognize the cross product formula here if you look at it. So like here's the 3 tensor gamma. You stick in VWX. You get out 1/6 gamma of VWX plus gamma of WXV plus gamma of XVW minus gamma of XWV minus gamma of WVX minus gamma of VXW. Close big parentheses. So if you wonder what I just did there, I cyclically permuted VWX. See, like basically what I did to come up with this pattern is I pushed W over 1. And when I did that, V comes back there. And then I pushed X over 1, and then the W went back. And then I did it in the opposite order, X, W, V, and then I cyclically permuted that. So I pushed the X off the edge over to there, and then I pushed the W off the edge over to there, and so that. And now I'll look at the book. I hope it's the same. Well, it's not the same order, but it's the same terms. All right. So that's the alternating on 3 things. And so a basic proposition is that if you have a alt alpha equals to alpha, if and only if alpha is antisymmetric, or in his language, alternating. So an alternating tensor is one which is completely antisymmetric, right? So there's that. Next up, he defines, so I'm trying to remember the notation we had. So alpha is like an element. Our notation for that was, remember it was lambda k v dual. This is the antisymmetric or alternating, if you like, k tensors. Well, it was k covariant tensors, right? K covariant tensors on V. And all right, so now he's going to build a basis for these things. So this notation's new to me, I think. Like I gotta be careful here because I don't want to say something that's not true. Actually, I'm really tempted to not talk about this part right now and to skip over to calculus 3. I'm this far in, let me kind of finish this here. So he makes a definition. He calls these the elementary alternating tensors. So definition, epsilon I is an element of lambda k v star, the elementary alternating tensor. And this is done with respect to a choice of basis. All right. So it's kind of like an anti-symmetric generalization of the dual basis idea. And the way he builds in the alternation is he uses determinate. So like specifically the formula is here. So like, so he's like, let epsilon 1, epsilon 2, epsilon n, basis for the dual. Then, and we have I a multi-index, all right? I is a multi-index, so it's like I1, IK, this is a length k multi-index. All right. And the assumption is that 1 is less than I1 ... IK. He does not assume necessarily that this is an increasing multi-index. So this allows repeats. There could be a repeated index here. But they have to be indices taken from 1 to n because that's our context. And so here's the definition. Epsilon upper I acting on a k-tuple of vectors v1 through vk is equal to, excuse me, determinate of epsilon I1 of v1 ... epsilon ik of v1. That's my first column. My second column is epsilon I2 of v1 ... epsilon ik of I should have put a 2 here, I believe. Yeah, 2. He doesn't have this written, so I'm adding something. There you go. Don't say I never did anything for you. There's something not in the book. Epsilon. Oh, that was an I1. I'm a dummy. Thank you. Your intuition is correct, sir. All right, vk epsilon ik vk, which is the determinant of like v1, the I1 component of it, v1, the ik component of it, vk, the ik component, the k, the I1 component of it. Or, well, anyway, yeah. So that is a that is a k by k matrix, right? But the vectors here don't have to be k-dimensional vectors, right? So if you think about what's going on here, and he has some specific instances of this. Like let me give his examples. So for like R3 dual, I guess this is example 1. I think some of these comments felt like examples, but I'll call this example 1. So if we're talking about R3 dual, right, which is the span of E1, E2, E3, right? And if we take like E1, 2, then we feed it VW. That would be the determinant of what? Oof. So I guess I do E1 of V, E2 of V, E1 of W, E2 of W. So that's like the determinant of V1, V2, W1, W2, right? But the point here is that V are three-dimensional, right? And W is also three-dimensional. So what we're doing is we've got some kind of machine to essentially calculate like subdeterminants. You know? It's in some sense a formalism to capture the notion of like the Laplace's expansion by minor for determinants. It's some kind of notation that it's getting at the same idea, you know? Because these are, it's allowing us to select like subdeterminants in n dimensions, you know? Anyway, so he has some theorems about that, like, let's see here. Oh my. And he defines, whoa, yowzers. So epsilon 1, 2, 3 is like the most you can get away with here. You know, past that, well, I don't know if it's clear or not, but past that it'd be 0. But if you do epsilon 1, 2, 3 of VWX, that just gives you the determinant. Like that. Because you'd have like 1, 2, 3 V, 1, 2, 3 W, 1, 2, 3 X, which is just VWX. All right. So his lemma, oh, by the way, he's got this like, he defines the Kronecker delta of a repeated index. Like if you've got a Kronecker delta of multi-indices, he gives a definition in terms of the determinant. It's on page 352. Just behold this monstrosity. That's very slick. I think I have seen that before, written in a much more gory notation. But anyway, let's not major in the minors here at the moment. Lemma 14.7.
Is that your musical morphism long for the day?
Yes. I do want to get back to the musical morphisms before we're done. So if you have a repeated index, it's like epsilon I is equal to 0 if, you know, like I sub j is equal to I sub l for some j not equal to l in the inside I, right? So like these are only non-zero if the indices are distinct. And long story short, if you look at just like the set E upper I such that I equals to, let's say I1, the IK, with 1 less than or equal to I1, less than I2, less than less than IK, less than or equal to n. So now I'm assuming we have increasing multi-indices, right? Increasing multi-indices. Then this is going to be, if I call this thing, let's say beta sub k, you could, I believe you could prove that lambda k of V dual is the span of this beta k. In other words, these elementary alternating tensors give you a natural basis for the set of alternating k covariant tensors over the dual space. And of course, we're really more interested in applying this to the cotangent space, right? So like when we apply it to the cotangent space, we're talking about our dual basis is like dx, right? Like for our principal application.